right, so hello, my name is Jacob, and welcome. I'm an industrial designer at Acorn Product Development, and for today, I'm going to be the moderator for the webinar. I just want to start by thanking all of you for joining us today. Although Teksun and Acorn, we've worked together for a number of years on a variety of different projects. This is our first time hosting a webinar together. We will be recording the webinar so that all of you can have access to the valuable information shared during the presentation, and we will send out those necessary links at the end. The reason we decided to come together is because the medical device industry is rapidly evolving, and we felt it was crucial for us to come together and exchange some insights, introduce some exciting possibilities within both teams. If you have any questions during the presentation, feel free to type them into the chat. I'll do my best to answer them throughout the presentation, or you can wait to the end and you can ask your questions directly to the presenter. For those of you interested in learning more about medical devices and development, this promises to be a pretty enlightening and informative webinar. We have a lot of experience to share with you, so I'm just going to go ahead and hand it off to Mohit on Teksun's side to introduce himself.
Thanks, Jacob. Hey team, over here it's Mohit Agrawal. Good evening and good morning to everyone. So I'm Mohit Agrawal, Head of Technology at Teksun, bringing over 11 years of experience in developing innovative solutions across various domains like defense, satellite communication, automotive, and agricultural domain. However, currently, I'm focusing on consumer electronics, particularly in medical, virtual assistance, edge AI, and security and surveillance field. Today, we are going to dwell more into the MIMO Radar based heart rate monitoring systems. Okay. So this is the MIMO radar system, which we have specifically designed for medical applications, such as the heart rate calculations. So before we jump into the specifics, let's establish what a radar is. Radar is short form for radio detection and ranging. It's a technology that employs radio waves to detect, locate, track, and measure various attributes of objects. MIMO is full form for multiple input, multiple output. That takes this concept further into MIMO radar system is multiple transmitting and receiving antennas or sensors are used to enhance resolution, accuracy, and robustness. This concept is extension of MIMO wireless communication adapted from radar applications. Now let's zero in into MIMO radar-based heart rate monitoring system. This system employs numerous transmitting and receiving sensors strategically positioned to collect reflected signals from the observed body. The main features of this are, it is a non-contact system. It's robust detection mechanism and high accuracy. And this is achieved through the key concepts of MIMO radar that are angle of arrival, azimuth plane, elevation plane, and time of flight. So now, why MIMO? So the answer to that is, firstly, it's multiple input and output that enables transmission of multiple signals, generating several beams or spatial channels simultaneously. So secondly, because of that, beamforming and directionality techniques, we can concentrate more on directing beams for increased accuracy. And because of this, the noises are reduced. The things that you see on the left-hand side are the three main pillars of the MIMO radar systems. And based on it, what we see on the right-hand side is range and coverage. It increases the range from 0.4 meter to 1.5 meter. And accuracies are on the lines of 95%. Now let's dwell more into what it takes. That MIMO is just a hardware property, but what happens throughout the course of judging or getting to an heart rate. So first it starts with transmission of radar signals. That is, low power radio frequency waves are directed towards the target. Then is the reflection and scattering, where the signals are reflected back by the body's tissue, including heart motions and blood flow. The third part is multiple antenna reflection, which is different antenna placed at different angles receive these reflected signals back. The main part of the MIMO is done in the first three steps. After that, what it comes into the picture is signal processing, where the signals that are received back, first of all, are conditioned and amplified. Post that, it is passed into the Doppler analysis. This technology examines Doppler shift caused by body motion, heart rate, and blood flow. So the thing is, it gets down to the sub-micrometer level to get to that particular understanding of what the movement is. Then it's feature extraction. Specific features related to heart rate are extracted from radio signals. Then comes into the play the fusion and integration of different kind of algorithms that we'll be discussing in the next slide. And at the end of all these 7 steps, finally we can get to the heart rate estimation and display, that is using extracted information from all these steps. The system calculates and displays the heart rate in beats per minute. So as we discussed in the last slide, that there are n number of algorithms that come into the play. The very first of them is Fourier transform, which is utilized to determine predominant frequency components associated with the heart rate. Now it's to understand that when we send out a particular frequency, it comes back, right? There would be a number of frequencies inside it. To filter it out and just focus on what the heart rate frequency is the main part, and that's what we do in the Fourier transform. Then comes the autocorrelation that measures similarity between a signal and a time-shifted version of itself. So this also plays a role in denoise calculations, where if a signal has been distorted because of some or the other reason, it can be correlated and taken into the considerations. Then it's about adaptive filtering, which is components are decoupled from the received radar signals using algorithms like Kalman filters. Once all of these are done, then it's time frequency analysis. In the Fourier, we talked about the frequency domain. Now it is time frequency, where again, to a certain extent, we use algorithms like wavelength transform, STFT, and other analysis of signal frequency content over time. And finally, when all the statistical analyses are there, you can reach to a certain number of accuracy. But post that, if you want to have other kind of, what I can say is, not just the heart rate, if you are just looking at heart rate variability or any particular aspects of it, any particular derived results of this, the machine learning can come into the picture, where techniques like support vector machine, artificial neural networks, and deep learnings can be employed with large data set of collection with obviously ground truth data attached to it. With machine learning, you can go into a step further with this traditional algorithms wouldn't derive. So that's all that comes into the play of calculating the heart rate from the radar signals. This particular product that you see on the left-hand side of the presentation is a MIMO radar, which Teksun has developed over the year of meticulous effort. On the right-hand side, you can see what Teksun typically provides. Teksun is a design house which provides end-to-end product development services, including hardware development, firmware development, mechanical, and IT-enabled services. The module that you see right now is a full-blown product, but we can also provide it into the module form factor. This product itself is BLE enabled, so wherever you see in your existing product, existing ecosystem, you see this can be fit. We can provide you with this particular product itself or the module that goes behind this particular product. So that's one service. And the third one is, since we have got so much of expertise in developing the algorithms and AI model development, which are customized for the use cases with radar sensors, and not just radar, given camera or any particular sensor. It could be vibration sensors and all. Teksun is very much strong into the algorithm and AI model development. So these are the three services that Teksun provides. Thank you. Handing it off to Jacob.
All right. Thank you, Mohit, for all that great information. If anyone in the audience has questions about MIMO, feel free to ask them in the chat. We're also going to have plenty of time at the end of the presentation to answer any questions as well. For now, I'm actually really excited to introduce Brian, the General Manager of the West here at Acorn. He's going to tell us a little bit about the requirements of taking a technology such as MIMO and developing it into a medical product. So take it away, Brian. On mute.
There, thank you. I'm Brian Lewis. I'm the General Manager at the West office here for Acorn Product Development. I've been developing complex medical devices and life science instruments and consumables for over 20 years, and I have degrees in both mechanical and electrical engineering. Many of these devices require development under an ISO 13485 quality system for FDA submission. And I'll explain some of the rationale for ISO 13485 and what it means for developing a medical device like we do at Acorn. So ISO 13485, what is it? It's the standard, the international standard used for a medical device development. And you always want to know, why is it important? What it does is it lays out a controlled and documented process that you follow as you develop a regulated medical device. And what it really is a QMS. QMS is a quality management system. So the quality management system does the job of spelling out how you do both your business and how you do engineering development. So there's a lot of important development processes, but there's also a lot of important business processes you follow when you lay out this system. And the way a company can become certified is that you have to develop a QMS, which is a quality management system that is tailored to your specific company and your approach. And then you have to train all of the employees how the processes work and what they need to follow as they go through this process. And then periodically, once you achieve 13485 certification, the company is audited by a third party to confirm that you're following your processes and that it meets the standards for 13485. So 13485 is really all about medical device development, and it's mandatory to follow this kind of a process in order to have the documentation and the evidence you need at the end of a development process. Good. So this is a waterfall development model shown here on the left. There's a couple of other types of development models, but this is probably the most common. And I'll go through this a little bit because it really has a lot of common elements, no matter what kind of development model you end up using. But it all starts with user needs, and you need to understand what is it that the user requires from this device that you want to build. And then from those user needs, you extract into the design inputs. What does this device have to do in order to meet the requirements of the users? So basically, design input means you're developing all of the requirements of the system. And then the next part of this is the design process. So that's typically where you're working through designing a new instrument, or maybe it's a consumable, but you're going through the design process, and you're trying to design the product so that it meets all of the requirements that you had in the design input. And then once you've done the design, then you can get parts made through design output. Design output could mean, schematics. It could mean drawings. It could mean CAD models. All of these are design outputs. And then you would go through and build something. And then you would evaluate it. It's called verification against the design input. So you're basically confirming, did what I end up producing do all of the things that I determined it needs to in that design input? And sometimes, you'll go back and forth and you might, during the review of your design output results, you might decide, that requirement needs to be modified a little bit, or perhaps I need to make an iteration on the design so that I can achieve that requirement. And then eventually, you'll go through the cycle, and you now have evidence that your design output is meeting the requirements. Then you can go to the next stage, which is the medical device validation. So you'll put together the device, and then validation really means that you're actually testing this device with real users, and you're confirming that it does what they need. So verification and validation are a little bit different, but they both have to be done before you can release a device through and get it approved by FDA and then market it for devices that require, FDA approval. So you have to follow a development model process, and at the end of this process, you have a complete documentation package, and that documentation package shows how to make the device. It shows the evidence that the device meets the requirements, and it has a complete package that can be used by a manufacturer to make the same device over and over again and have it work. So a couple other important parts of the development process for a medical device. Risk management is extremely important, and it's one of the first things that FDA looks at, and it really needs to be the one of the guiding principles of how you do development. So you have to assess the risk of the device, and then you have to mitigate risks. For example, you could have a potential where you have a bad reading, and it could give you a bad result. Maybe in this case, a bad heart rate count. You have to look at these possibilities and find a way to mitigate it. Maybe it's mitigated in a sensor design. Maybe it's mitigated in software. Whatever the mitigation is, it's got to be enough to make it safe to use. And then for design and development, you have to follow a phased-based design and development process where you have reviews after each one of the phases that you go through. And different firms will have slightly different design and development processes, but they all typically follow this phased orientation, and they require you to do development and documentation as you go according to your QMS, which is all of your procedures. So applying 13485, if the products based on the Teksun technologies, the MIMO that we just heard about, are intended to be medical devices, following the definition of FDA, if it's class 1, class 2, it probably wouldn't be class 3, but if it's class 1 or class 2, they have to be developed under ISO 13485 and follow the FDA guidelines, for those classifications. If it's a class 1 device, it's not as rigorous. It still has to follow, processes. If it's class 2, it's substantially more rigorous. There's more focus on safety. And then, class 3, which we won't have to deal with this product, that's another step even further. So understanding this 13485 standard and how you control the design is really essential. So some of the key parts of it are risk management, the development process, following the proper sequence and developing the proper documentation, mean, all of this is evidence for when you submit to the FDA to get your device approved for being marketed. You have to have all of this evidence, and they expect to see, this complete package, which is usually called a DHF, a design history file. So that'll have everything in it. When you do testing, you need to use calibrated test equipment, and you need to generate the right kinds of reports and test protocols, and have the evidence clear that you met your requirements. And then you have to have all of the other parts, which includes processes and systems for things like purchasing, environmental controls, shipping and receiving, corrective and preventative actions. All these different parts of a QMS have to exist, and you have to be able to show that you follow them. And then at the final part of your product development, you have a complete DHF, a design history file. And that's essentially everything. It's your evidence that shows that your device meets its requirements. It also has all the build instructions. It has all of the drawings, all the software. It's sort of everything about that product that you've developed. So I hope that helps explain a little bit what this is meaning to do, this 13485 that you hear about a lot. It's basically your own process that you have to be audited against and show that you follow your processes, and that it gives you all of the controls that you need in order to be acceptable for when you submit to FDA to get your device released for being able to be marketed here. It also applies to Europe and Asia, by the way.
Yeah. All right. Thank you, Brian, and everyone for participating. As mentioned, we're going to share the link to this presentation and the recording after the webinar. But for now, I'd like to open up the floor for any questions the audience may have. All right. If there are no questions and no final words from our presenters, I'd just like to thank everyone for coming. You can learn more about Acorn and Teksun.
Jacob, I'm having one question. So, may I ask?
Yeah, go.
Hello? Yeah. So, what are some real-world applications of MIMO radar-based heart monitoring system?
Mohit, would you like to answer that?
Yeah, certainly. Thanks, Hardik, for asking that question. It's an interesting one. So certainly, MIMO radar monitoring has found success in various industries. In healthcare, it is used for continuous patient monitoring, fall detections in elderly, sleep apnea detection. It also finds its use case in automotive safety. It is employed for driver monitoring and vital signs monitoring. In agriculture, it could be used for crop health monitoring. And it can be even used in security and surveillances, where whenever you want to see through the walls, right, that's the main feature of the radar, that no violet frequencies or ultrasound frequencies or the cameras, whenever they can't go through the walls, this particular technology can go through them and have n number of use cases. So when you go with imaging radars, they can get into actual replacement of cameras where the picture quality is not the concern, but getting outputs from it is the concern. So from that perspective, radars are really useful. In one of the use cases, it can identify intruders. It can monitor crowd behaviors. It can calculate the footfalls in a particular hotspot domain. That could be done. So this particular technology is particularly very versatile. And in this particular call, we just chose to take up on the sides of heart rate, which makes it a lucrative kind of endeavor, where generally heart rate calculation is attached with having some or the other kind of equipments attached to the human body. When it's a personal one, no issues. But when it goes into the medical, not everyone likes to use the same equipment where the hygiene gets into the picture. So that's one of the angles we wanted to instance. Yes, Benjamin.
Thank you, Mohit.
Thanks, Adit.
All right, so this has been a question for those teams. Since we're talking about medical product development, and the last question has gotten into use cases and usability and such. How on Teksun and also on the Acorn side factored in usability, particularly in hardware development and also from your hardware medical product design and development process.
Got you. Thanks, Benjamin.
Yeah.
So,
As a designer, I kind of touch a little bit on that. So as Brian mentioned on that waterfall, one of the first requirements is user requirements. And as a designer, we go in and look at the UX, user experience, try to find those requirements and opportunities where a user would actually navigate the product as well as their environment. From there, we make those requirements and we maintain and use that as the foundation for the entire design process. So we make sure we keep the users in mind from the very beginning and we have checks and balances along the way. Brian, you can answer anything that you think I may have left out, but then hopefully that gets the answer across.
Yeah, I think so. User needs are a lot of things, and different products have different user needs, so they all need to be considered. It could be, there's a lot of different elements, and it really depends on the particular application.
I see another hand raise.
Yeah, hi.
Feel free to ask your question.
From Solution Ahmedabad. I have a question regarding data privacy when it comes to using user data to train or further train the AI algorithms. How do you make sure that you're not or you are being transparent to the user, that user know what kind of data is being used and how it is being used?
Thanks, Ajay, for having this question on the privacy. And we do understand the challenges with it. And that's the main reason that we have moved towards the radar-based approach instead of the cameras, where generally it is more intrusive into the lives of the particular individual. So when it comes to radar, it is not taking away any particular image, or the imaging that happens is in terms of point clouds only, that generally doesn't disclose any particular private information. So that's from the technology aspects. And apart from that, privacy and ethics are important consideration while implementing radar-based health monitoring systems. These systems can capture detailed psychological information, and it's crucial to handle this data with care. So that is particular thing, that the information that we are particularly deriving is something to that particular person, and that needs to be like a privacy needs to be maintained, and it's particularly on the ethics based that are being laid under the GDPR and HIPAA compliance. So we do follow all of them so that none of the derived parameters even that are captured are being used for any particular purposes or not. So I hope that answers your question. Yeah, Jignesh, I see your question. Currently, we are in process of doing a certification for this particular product.
All right. If there are no further questions,
Jacob, I see one question in the Q&A section that it states that how does MIMO radar heart rate monitoring compare to traditional methods like ECG or PPG? So that's an interesting question, Jenna. So It's that MIMO radar-based heart rate monitoring offers certain advantages over traditional methods like ECG and PPG. It provides continuous non-contact monitoring. That's the main feature about the radar, which can be more comfortable for patients and doesn't require direct skin contact. So that's the main leverage the radar has over the PPG. It's in terms of the comfort, and however it can capture heart rate even when ECG electrodes or PPG sensors might not be feasible, such as remote monitoring scenarios. Like I shared the particular use case of like driver monitoring scenario where you would be having a particular dash cam in front of you. You have a user driving the car, and while the car is being driven, you need to monitor the state of that particular driver because it has been observed that reason of many accidents is identified as driver fatigue, and the heart rate and all those kind of vital informations are generally attached to the fatigue kind of information. So in that particular use case, uh, this can prove to be useful. And when it comes to the particular accuracy and reliability, that may vary upon different factors. But when it is the PPG or ECG isn't touched, I would say that they would be at better accuracy. Okay. Other question I have again from Hardik. It is regarding can you provide examples of successful applications where MIMO radar based monitoring has made a significant impact on healthcare or other industries? Okay. Okay. I guess that's the same question again, Hardik. We answered it on the sides of that, not just the healthcare, it gets into the patient monitoring, fall detection, and the sleep detection areas, crop health monitoring, and all those stuff. I guess we get covered this earlier. Let me check if there. So yeah, I have a question from Paris as well. How accurate is radar-based vital signs? Currently, we are at an accuracy of 95% with the radar, and generally other methods also fall on the brink of, because there is always from company to company there would be a bit of offset of, I guess, plus minus 3 or 4 percentage. So I guess we fall uh, like on the same segment when it comes to the accuracy. Yes, Bhavin. Bhavin has asked an interesting question that uh, does it detect multiple person at same time and then work? It depends upon the kind of radar that we are taking. It's not just the MIMO. MIMO is just the aspects of a particular antenna, how that particular antenna, the transmit has and the receive has been made. There are multiple technologies in the uh, radar side as well, namely pulse current radars are there. Then we have frequency modulated radar. Then it is continuous wave radar systems are there. So that's the main technology also behind it, how the waves have been transmitted. Coming back to your question on multiple persons, it depends if you are able to do the point cloud. You are able to do the point cloud very well, and with spatial, like if a person is just here, you can make leverage of the specific direction of arrival and all those things. Then you can identify this point cloud is at a bit of a distance from here. Yes, you would be able to identify multiple persons. Okay, so we have another question from Sheetal. where she has asked that if there are any applications that things needs to be taken care in design. So yeah, the main focus of the session from Jacob particularly was on the ISO 13485 is on the sides of what process do you follow from the medical standpoint. Being a non-intrusive device which doesn't touches the particular patient, and these are just a portable devices. From that perspective, we fall into the class 1 category. So based on that, whatever is needed to be followed on the ISO 13485 has been followed at our end, and we are still into the certification phase with it. The processes have been started for it. We are waiting for the certification to be approved.
Yeah, that's a really good question. There are tons of things to consider when a device is on the human body. Wearable medical devices is actually a really big growing industry that we're seeing a lot of now. You have to pay attention to ergonomics, how the device is charged. Most of the time you want to make sure that the device cannot be charged while on the human body, just to get rid of any of those safety concerns. Brian, again, he can answer this more in depth in terms of ISO, but it's a very good question. I think there's a ton of opportunity to explore. It's really the interaction with the device. Once you go from a device that's off the body, where you are interacting with it so many times a day, versus when something's on your body and you now have to live with it, 24 hours a day, there's a huge difference in design considerations and how in depth you have to go. So we got another question. Are there any other methods as well where you can have wireless and non-contacting monitoring? Okay.
Sure. Thank Jadip. That's another good question coming from your end. So certainly there are 3 other common and efficient methods used, such as impulse radio, ultra-wideband radar systems, continuous wave radars, frequency modulations on other technologies. So yes, there are multiple technologies that can be used in non-contact monitoring.
All right. Well, thank you everyone for asking questions. They were really great. Hopefully we were able to answer them all in depth. If you have any additional questions, you're welcome to reach out to Acorn or Teksun. You can visit our website and learn a little bit more about our capabilities. Yeah, we're going to send out those links at the end of this call. And thank you all for participating. Yeah, and have a great day.